I hope everybody is doing well. So this is the enzymes lecture for year 1 students. So I'm gonna start immediately. So what are enzymes? So enzymes are proteins. They provide an environment that is energetically stable for reactions to occur. Now, what does that mean? In a cell, it is energetically non-favorable for reactions to occur. That's just how nature is. But then we developed to have enzymes that make this environment energetically stable and favorable for reactions to occur. Okay? So, what do these enzymes do when substrate binds? They form product. So, an enzyme plus a substrate gives us a product. They are selective. What does that mean? It means that an enzyme only binds to a certain substrate. It's only specific to this substrate, nothing else. So what does this enzyme do to the reaction rate? Well, it depends on the type of reaction. It might either increase the rate or the speed of the reaction, or it might decrease the rate of this reaction. Okay? So do they consume or alter anything in the reaction? Of course they don't. Of course not. They just speed it up or they slow it down. Okay? Are all enzymes proteins? Yes, but there's an exception called a ribozyme, which is an RNA that can act as an enzyme or like an enzyme. Okay, so what are cofactors? So cofactors, from the name, co means with, and factors is just elements or compounds. So these are molecules that come with the enzyme or they surround the enzyme. So what are the types? It might be organic or it might be inorganic. So what are organic cofactors? They are called coenzymes. So cofactors, when they're organic, they are called coenzymes. Cofactors, when they're inorganic, they're metal ions like magnesium, copper, whatever. So what are coenzymes derived from? Coenzymes come from vitamins such as NAD, FAD. I don't think you took these yet, but you'll take them later on. For now, just know them as examples. Okay, so we know what cofactors are now. Now, what is a holoenzyme? Now, a trick that I always use to help me study is that if I see a new word, I Google something called the Greek origin, if it's from Greek. So holo comes from the Greek word holos. And what holos means is that whole, okay? So this word means an enzyme that's a whole. Yani it's complete. What that means is that this enzyme is complete. A holoenzyme is complete, which means that all its factors that make up this enzyme are there. In this case, the holoenzyme is made up of an apoenzyme, a coenzyme, and an inorganic cofactor. As we just explained, these are the cofactors. We have an inorganic and an organic, which is called a coenzyme. So a holoenzyme, okay, is an enzyme that is a whole, okay? It has all its constituent, let's say elements, okay, that make it a whole, okay? So now we're gonna explain the other element of this holoenzyme, which is apoenzyme. So what is an apoprotein or an apoenzyme? Apo comes from the Greek word off or away. What does that mean is that this apoprotein or this protein part of the enzyme is off. It's not turned on unless it's bound to the other elements, okay? So in the holoenzyme, we have the protein part, which is the apoprotein, this part. This is the protein part in blue, okay? And then we have the non-protein part, which is the cofactors, the coenzyme and the inorganic cofactor. So the part of the holoenzyme, which is the apoenzyme, that is turned off is this one. And it's only turned on when it's bound to the coenzyme and the inorganic cofactor. And when they're all together, it's called a holoenzyme. I hope you really understood this. And if you didn't, then rewind. Okay, so moving on. What is the difference between simple enzymes and hollow enzymes? Simple enzymes are those that don't need these factors, these cofactors. Their amino acid side chain is enough to activate it. Hollow enzymes, of course, it needs these cofactors for it to be activated. The apoprotein is not enough for it to be activated. Okay? So, to elaborate on coenzymes and metal ions, as we said, coenzymes are organic and they're derived from vitamins. Can they bind to substrate too? Yes, coenzymes can either bind to the enzyme or to the substrate. Okay? Now, for how long? It's short and they're easy dissociable. Okay? So, what is the role of the coenzymes? Number one, they carry groups. So, for example, in this case, the group that I put an example for you for is H+. So, for the cell to respire, there needs to be a shuttle of proton network يعني. What that means is that there's a proton or an H+ that's carried by a lot of intermediates for it to form something called ATP, okay? And this proton is carried by certain groups that are enzymes. And in this case, it's coenzymes, that is NAD, okay? So NAD carries this H+, okay? And this H+ is given for formation of ATP, which is essential for cellular respiration. And what cellular respiration means, it's just the formation of energy to sustain life within the cell. Now, the second role is similar to the first role. It actually completes the first role. And what it does is that it stabilizes reactive species. What that means is that H+, if not bound to NAD or not carried by NAD, it's going to be alone in the solution. And that's bad because it might cause damage, tissue damage, what I mean. Okay? Now, as we said, coenzymes, they carry these groups. They stabilize these groups. And the last role is that these coenzymes, they actually help in the recognition of the enzyme. So this is an enzyme that doesn't have a coenzyme, but this enzyme has a coenzyme that's right here. So what happens is that the substrate can easily find this enzyme and it's easily recognized. Okay? I hope this makes sense. Moving on. Moving on to the classification of enzymes. So we have, I think these are six classes of enzymes. The first one is oxidoreductases. So if you remember from high school chemistry, you should know that you have oxidation reduction reactions. They involve the gain and loss of electrons between molecules. So these enzymes are the ones that take these electrons and transfer them from a group to the other, okay? This is the first one. The second one is a transferase. They transfer groups from donors to recipients. From its name, a transferase, it transfers groups, and an exception here is hydrogen. It does not transfer hydrogen. Hydrolases and lyases. These two have the same role. They break down bonds. So A and B, you have a broken bond. But the difference between these two is that hydrolases catalyzes or it just uses water, H2O, to break down this bond. However, lyases, it doesn't use water to break down this bond. This one uses water, but this one doesn't. But they both break down bonds. So we have, which involves gain and loss of electrons, transferases, transferring groups, breaking down bonds, involving water, not involving water. And then we have isomerases. So isomerases are enzymes that catalyze the transfer of groups within a molecule to form isomers. So what are isomers? Isomers are molecules that have the same molecular formula, but different structural formula. For example, you have C4H10. C4H10 can be called butane or isobutane, right? These two are not the same compound. They have the same molecular formula, which is C4H10, but they have different structural formula, and that is exactly what an isomer is. Okay? So isomerases are enzymes that make isomers. Okay? So another example that I have here is that UDP glucose and UDP galactose. When isomerases move around the carbon, it can make it as a glucose or as a galactose. These are isomers. Okay? The last one is ligases. Ligases comes from the word ligate. And what ligate means is to stick something together. And that's exactly what it does. In opposition to lyases and hydrolases, ligases forms bonds. It uses ATP to make this bond, of course. Now moving on to the nomenclature. So, the first one is xanthine oxidase. What does xanthine oxidase mean? Oxidase means that this is an enzyme that oxidizes the substrate. What is the substrate? Xanthine. Makes sense. A kinase is an enzyme that adds a phosphate group. What that means, it's just phosphorylates. Another word for it is phosphorylation. Phospho as in phosphate, relation is adding. So when an enzyme adds a phosphate to another group, this group might become active or deactivated. It depends on the reaction. But this is what the name means. Now, pancreatic ribonuclease. Pancreatic means this enzyme is secreted from the pancreas. Ribo means RNA. Nuclease means I am breaking down this RNA. So this enzyme is an enzyme that's produced by the pancreas that breaks down a nucleic acid called RNA. Okay? Cysteine protease. So, from its name, prote is protein. Ase is cleavage. So, I am an enzyme that breaks down proteins. What's the protein? Cysteine. In this case, it's an amino acid. Now, hormone-sensitive lipase. So, lipase, lipid, yani fat, which means fat. Ase is cleavage, we know that. So, I'm an enzyme that breaks down lipids. But I am hormone sensitive. What does that mean? It means that I am regulated by hormones. It means that hormones either turn me on so that I can break down lipids, or turn me off so that I won't break down lipids. Okay? Now, this is an example that was found in your lecture. So, this enzyme is hexokinase. And what hexo means, it means it has 6 carbons. And kinase, as we just explained, it means that we're adding a phosphate group via this enzyme. This is another naming for this enzyme, which is pretty long, but it's easy to understand. D is the orientation of this molecule, or how this molecule looks in space. This is actually not biochemistry, it's organic chemistry, but if you're curious and you want to know, D means right. It means that this molecule is oriented to the right side in space. And another type is called L, which means left. So the molecule is either oriented towards the right side or to the left side. Okay? As we said, hexose means 6 carbons, and this 6 means that the reaction is happening at carbon number 6. Phosphotransferase means that phosphate is being transferred. Okay? So this 6 carbon molecule is transferring phosphate at carbon number 6. Now, this naming is created by the Enzyme Commission. It actually describes this enzyme, but in these terms. So EC stands for Enzyme Commission. 2, it tells us the class of this enzyme, and of course, it's a transferase. 7 tells us that this enzyme is transferring phosphate, and 11, the first one stands for that it's transferring this phosphate to alcohol, and the last one tells us that it happens at carbon number 6. If I were you, I would not study this, because back then I didn't even study this one. But if your professor said in class that you should know this, then you should know this. But for me, I don't find it important at all. I just want you to make sure that you understand everything that I said here. You need to understand everything that I said here. But this one, I don't really care about it personally. But if your professor said in class that you should know it, then You probably should. So, moving on to the active site of the enzyme. So, what is the role of the active site of the enzyme? As I said in the beginning, enzymes provide a suitable environment for reactions to occur. So, this is the active site of the enzyme, and one of its roles is that this is the place where the suitable environment is. Okay? This is the first role of it. The second role of it is that it brings this, if you see this substrate to a closer proximity to the enzyme itself. So it looks like a pit, if you can see right here. This is the active site. It looks like a pit. And this is another role of it. So why is it 3D shaped? It's 3D shaped because of the folding of the acyl groups. And why is it shaped like a pocket or a pit? It's shaped like that because this protects the substrate from solvents in the solution, and as I said, it brings it to closer proximity. So the enzyme actually has a binding site and a catalytic site. A binding site, there is no reaction here. There's no reaction. It's just a place where the substrate can bind. And the catalytic site is actually the site where the reaction occurs. Now, these are examples that I took from your lecture. The first one is chemotrypsin. And what happens is that this type of pocket or this type of active site is called a hydrophobic pocket, which means that it only accepts hydrophobes or lipids to react. The second one is for trypsin, and the active site is a salt bridge. And what that means is that negatively charged amino acids can bind to positively charged amino acids. So if you have a negatively charged here, it won't bind. It won't happen. Okay? And then the small hydrophobic pocket has certain molecules that block the entrance to the active site, and it only allows amino acids with small side chains to bind. So this actually affirms what I said in the beginning regarding enzymes being specific to certain substrates. So now moving on to conformational fits of enzymes. We have two types, Emil Fischer and Daniel Koshland. Emil Fischer is that a type where the enzyme and the substrate, like a lock and key, they fit exactly right into each other. However, the Daniel Koshland type means that they change to fit each other. So if you look right here, the enzyme does not have the conformation for the substrate. So what it did is that it changed its active site or how its active site looked so that the substrate can fit. An example that was found in your lecture was regarding hexokinase. So as I said in the beginning, is that hexokinase is an enzyme that adds phosphate to glucose. And what happens is that if glucose is not found in the medium, if hexokinase cannot bind to glucose, what it does is that it changes its shape so that water doesn't bind and react with it. Okay? And this conformational change ensures that hexokinase will only bind to glucose. So this also ensures what I said in the beginning, that enzymes are specific for their substrates, and they will change if their substrate is not there so that nothing else will bind to them. Okay, moving on. So now moving on to the kinetic theory. And for two molecules to react, we need to have certain conditions to be met. Okay? The first one is that they should be oriented towards each other. Yani, if one of them is oriented towards the left side and one of them is oriented towards the right side, then that's wrong. They need to be oriented towards each other, right? And the second condition is that they need to be close to each other, because if they're far away, the bond will never form. And the last one is that they need to have increased kinetic energy. And what does kinetic energy mean? Kinetic energy means motion. And motion is just their movement. So, with molecules, there's a barrier that they need to overcome so that they can react with each other and form a bond. When they have increased kinetic energy, they can actually overcome this barrier easier, okay? And to make it easier for you, if you think of boiling water, what happens is that you're increasing the temperature of this water, right? And when you increase the temperature, the molecules, or the H2O molecules, their kinetic energy is increasing, which means they're moving faster in the water. And that's how you see the bubbles forming, because what's happening is that they're forming bonds with each other very fastly. So this actually explains what I just said. So the barrier right here needs to be overcome for them to form a bond with each other. And to overcome this barrier, they need to have increased kinetic energy. And what kinetic energy is that they need to have increased motion. And collision is just them overcoming this barrier and colliding with each other, yani forming the bond, okay? Now, before I get into enzyme kinetics, which is pretty long, and you need to understand these basics first, okay? So let's say we have two reactants, A and B, that react and form products that are called C and D, okay? When you see this, it means this reaction is not reversible. It means A and B for sure will become C and D, but C and D cannot come back to become A and B. But when you see this, it means that A and B can become C and D, and C and D can go back to being A and B. This means it's a reversible reaction. This means it's not a reversible reaction, okay? So we have something called K, which is a rate constant that is just a constant that we use in all of the equations that I'm going to state in a bit. And the rate, which means the speed, is calculated by multiplying the rate constant times the reactants, okay? So if you want to calculate the rate of the forward reaction, or the reaction that's forming from A and B to become C and D, you calculate something called K1, because you're going in this direction. But if you're going in this direction, you calculate something called K minus 1. When you're coming from C and D to A and B, you calculate K minus 1. When you're going from A and B to C and D, you calculate K1, okay? So what is the rate equal to? The rate of K1, or the forward reaction, is equal to the K1 times the concentration of A times the concentration of B. Now, don't let these little A's and B's intimidate you. These don't matter for you, to be honest, because they are just stoichiometric coefficients. They help us, actually in organic chemistry, they help us stabilize the chemical reaction to make the concentrations equal, okay? So we calculated the rate of the forward reaction, and as I just said, the rate of the reverse reaction, K minus 1, okay, is equal to the rate constant, of course, times the concentrations. Now, what is K equilibrium? K equilibrium is when the speed of A and B becoming C and D is equal to the speed of C and D coming back to A and B, okay? Now, in this case, that means that the rate of the forward reaction is equal to the rate of the reverse reaction, right? Because these guys are becoming these guys at the same rate that these guys are becoming these guys. Make sense? So K1 would be equal to K minus 1, or R1 is equal to R minus 1, okay? If you see right here, so K equilibrium is equal to R1 equal to R minus 1. If you just do some math, you can see that K equilibrium is going to be equal to K1 over K minus 1. So activation energy, what is activation energy? As I said before, for molecules to form a bond with each other, they need to overcome this energy barrier and have enough energy so that they can form a bond with each other. This energy that they need to have is called activation energy. Okay, it's the amount of energy needed to start a reaction. Okay, so what yields this energy in enzymes? Weak interactions. So if you look right here, these weak interactions, they give us this activation energy. between when the substrate interacts with the enzyme, they have weak interactions at first. And these weak interactions are the ones that help them overcome this energy barrier and form the bond. Okay? So, what do these weak interactions cause so that the bond is permanent? Number one, what happens is that as the substrate becomes close to the enzyme starts changing its shape so that it can fit perfectly to the substrate, thus being more specific to the substrate, right? Then, when they bind to each other, okay, this releases something called binding energy. And to help you remember what binding energy is, in chemistry, energy is neither created nor destroyed. It's only transferred. So as I said at first, there's something that they need to overcome their energy barriers, which is activation energy. This is the investment energy they have. But when the bond has formed, they have to release this energy that they used. They have to pay their debt because energy is neither created nor destroyed. It's just transferred. So they use activation energy and they release what? Binding energy. Okay? Now, when they bind to each other, actually, the entropy of the substrate decreases. Now, what is entropy? Entropy is motion or the movement. And this actually makes sense because when the substrate binds to the enzyme, we don't want it to be weak interactions. We want it to be strong covalent interactions to stabilize this complex and for the reaction to occur smoothly. If it's not stabilized, then that's not okay. And for it to be stabilized, we need the substrate to have restricted motion. It should not move at all. Okay? Now, the last one is desulfation of the substrate. And what does that mean? If you look right here, you see these small water molecules that surround the substrate. When they realize that there are some weak interactions starting to form between the enzyme and the substrate, they move away so that reaction can be easier for the enzyme and the substrate. Okay, so what is the transition state? Now, as I said before, enzyme reacts with a substrate to give us a product, which is right here, right? Now, this is the transition state. It's the state where the reactants have absorbed enough activation energy for them to transition to this phase, which is the enzyme plus the product. Okay? So, in this case, this is the transition stage where the enzyme reacts with the substrate, and in the transition state, they are still within each other, but here they have enough energy for them to separate into enzyme plus product. And the L is just a byproduct that's released. What does activation energy have to do with transition state? Actually, in the transition state, the energy that's being increased is what? It's activation energy, right? Because they use activation energy to form bonds, and then when they form the product, what is released? Binding energy. In this case, activation energy is equal to the initial energy, which is this one, minus the energy in the transition state, which is this one, right? So if you want to know exactly what the activation energy is, you need to subtract the initial energy of the reactants, which is the enzyme alone and the substrate alone, minus the activation energy that is in the transition state. Now, before I enter into these enzyme kinetics, I want to explain these here first so that it can be easier for you to comprehend what I'm gonna say. As S increases, what happens to the reaction rate? Speed. So what is S? S is the substrate, right? And E is the enzyme. So as S increases, the reaction rate should increase. Why? Because more free enzymes are being occupied by substrate, and they all of them are becoming in the transition state. And when they're in the transition state, this increases the rate of the reaction because why? more product is forming, right? So the reaction rate is gonna increase as you increase S until it reaches something called Vmax. Now, what is Vmax? Vmax is the maximum rate an enzyme can operate. So if you look right here, you have 3 enzymes and you have a lot of substrates. So if you put, let's say, 6 substrates, these enzymes won't have an increased rate because their capacity is to work on 3 substrates. If you give them 6, their Vmax will not increase. Their speed will not increase because only 3 and they can work on 3 at the same time. When they're done with these 3, they can work with the others. But if you give them more than their capacity, they won't work. Okay, so this is what Vmax is. And if you increase the substrate, the reaction rate will increase until it reaches the capacity of the enzyme, which is Vmax, the maximum speed. Now, if you ask me, when do I measure the enzymes? Like, when do I measure the concentration of this enzyme in my beaker, for example? It would make sense that you should measure the enzyme concentration when the enzyme is occupied, when the enzyme is bound to the substrate, not when it's free. Okay? So, you measure the enzyme when there is substrate excess or increased S, so that means it's occupied, check. And you measure it when the forward reactions are dominant, when E plus S is going forward, not going backward, when more enzyme is being occupied, not being free. So the more occupied the enzyme, the easier it is to measure its concentration or exact concentration in solution. So to reach Vmax, S must be increased. So this curve shows us the initial velocity V naught, and we have something called Km. I'm gonna derive it for you in a second. And then we have this curve or hyperbolic curve, and at some point it's gonna reach a Vmax where it will never go over because the enzymes have certain capacities that they cannot overcome. So now that I have explained what Vmax is and how you can measure the concentration of enzymes, I'm gonna go back to enzyme kinetics so that I can derive Km and the Michaelis-Menten equation so that we can explain these after. So I'm back here. So I explained these down there. So what is Kd? Kd is dissociation constant. And what does that mean? It means that this constant shows us the affinity of the enzyme to the substrate. And what does affinity mean? Affinity means the likelihood of this enzyme to bind to the substrate. The more affinity an enzyme has to a substrate, the more likely it is to bind to this substrate, and vice versa. The less affinity it has, the less likely this enzyme will bind to this substrate. So the higher the Kd, or the higher the dissociation constant, or the higher the possibility that the substrate will dissociate from the enzyme, the lower the affinity, of course, because the higher the possibility that it unbind from this enzyme means that the enzyme has low affinity to this substrate. It doesn't like this substrate. But the lower the dissociation constant means the lower the dissociation probability, or the lower the possibility that the enzyme will separate from the substrate, means that the enzyme likes this substrate and it has increased affinity to it, so it will not dissociate. So that means the higher the Kd, the lower the affinity, the lower the Kd, the higher the affinity. Now the derivation of the Km and the Michaelis equation. So basically there's a lot of math here, but what I want you to understand is that to derive the Michaelis constant, you need to work with these equations until you reach these 3 constants together. That's how you derive Km. And for Michaelis-Menten equation, you need to find V node, which is the initial velocity. Okay, and I'm going to explain each of them separately, but for the math, I don't think it's important for the exam. I just want you to understand everything that's happening here and how it's being derived. But as for knowing the exact details, I don't really find it important, even though back then when I was in your class, I did actually study the derivation. But if your professor told you in class that you should study this, then you should. But for me, I wouldn't study this unless the professor told us to. What you should study is what Km is equal to and what the Michaelis-Menten equation actually is. Now, the derivation, I wrote it because it's explained in your lecture and I will explain it right now. Let's go back to the thing that we've been talking about from first. Enzyme plus substrate. Transition state gives us enzyme plus product. Forward reaction, reverse reaction, reverse reaction. K1, K2, K minus 1, K minus 2. Okay? So, the first assumption we're going to make is that we are at the steady state. Now, this is similar to a word that I explained 5 minutes ago called K equilibrium. What is K equilibrium? K equilibrium means that the rate of formation is equal to the rate of dissociation. It means that this concentration is constant. The concentration of this is constant. It means that these becoming this is equal to these becoming this. Okay? So if we are in the steady state, it means that the rate of formation is equal to the rate of dissociation. Now, what is the rate of formation? As I have explained before up here, rate of formation of the forward reaction is K1, or the rate constant, times the concentration of reactants, okay? And the rate of the reverse reaction, which is this one, is K minus 1 times the concentration of reactants. So if we go back right here, so rate of formation of ES. What reactions are forming ES? They are this one and this one, right? K minus 2 and K1. So how do you get K minus 2 and K1? R1 in this case is equal to K1 times the concentration of E times the concentration of S, which is right here, which is right here. R minus 2, which is this one, it's going this direction, is equal to K minus 2 times the concentration of E plus P. But in this case, you see that I did this. I considered R minus 2 as negligible. Why? Because in this case, the beaker is right here and I have just put the enzyme and substrate in the beaker. It's too early for the enzyme and product to form. That's why I'm saying that K minus 2 is actually negligible, because it's actually not there yet. We're not there yet. It's too early for it to form and for it to come back to the transition state. So we find this negligible. Rate of formation is equal to the rate of dissociation. So the rate of dissociation is ES becoming this and this. So it's R minus 1 and R2. This and this. Okay? And since this one is negligible, R1 is going to be equal to R minus 1 and R2. We just put the reactants and the constants, as I have just explained it, how. And now, since we're deriving Km, we need constants in this, right? So we are gonna get something called E total. Now, what is E total? E total is the total concentration of the enzyme. And the total concentration of the enzyme, since we are still in the beginning, is equal to the free enzyme in solution and the enzyme that is bound to substrate. If this reaction was at T equal, for example, 60 or 80 or 90 minutes, we would not have used free enzyme, because all of them will most probably be bound to a substrate. But in this case, since we are at T equal to 0, that we have just begun this reaction, then that possibly means that we still have free enzymes in the solution. So what I did was that I wanted the E, so I rearranged it, and we get E is equal to ET minus ES. And then after that is I just substituted it in this reaction that we derived a minute ago. So it's gonna be equal to this. You just substitute this here. So E, these will become here. It's supposed to look like this. Now, what I did is that I just expanded, okay? And this is how it looked like. Since I reached two of the constants, I still have only one constant for me to derive Km. So what I did was I divided both sides by K1, and thank God I got this, which is Km. I have successfully derived Km. Now we need to move on to deriving Michaelis-Menten equation. The first step that I did was that I rearranged it. So instead of this whole thing, I put instead of it Km, and I started with ES. Since here it's minus 2, I move this to the other direction and it should look like this. And in the second step, I took ES as a common factor, and it should look like this. And then since I only want ES, I divided by S plus Km. Okay, and when you divide it, you get ES is equal to this. Now we're very close to the end. We just derived this, and we need to remember that V is equal to V node is equal to K2 times ES. Since, as I told you in the beginning, that Michaelis-Menten depends on V node, so we need to turn this into something similar to V node. But what is V node equal to? We know this from the beginning, that V node is equal to K2 times ES. In this case, we only have ES, so what do? Times K times K. So the equation becomes K2ES is equal to K2ET times S over Km plus S. So now the last thing we're going to assume is that V node is equal to Vmax. And what that means is that the speed where all the enzymes are occupied, which means that E total is going to be equal to ES only, without free enzymes, because all of them are occupied. Since we are at Vmax, this means this is the maximum rate an enzyme can operate. There is no free enzymes, as I have just explained a minute ago here. So V node is equal to Vmax when ET is equal to ES, because all the enzymes are occupied. So what you can do is that just substitute K2ET by Vmax. So what happens is that V node is going to be equal to Vmax times S, this one, over Km plus S. And this is actually the Michaelis-Menten equation. Now, if I were you, I would definitely not study this derivation, but I derived it for you so that you can understand what's happening and how the scientists thought about it. But for the exam, I would personally just study this, deriving the Michaelis constant, and this, which is the Michaelis-Menten reaction. If your professor, as I said before, if your professor said in class that you should know the derivation, then you should. But if she didn't, I don't recommend it. Now moving on to the graph. So we derived Km, but what is Km? What is it exactly? I know it's a constant, but chemically speaking, Km is Vmax over 2, which means that it's half the speed or half the maximum speed that the enzyme reaches at capacity. So at maximum capacity, as I said right here, the enzyme reaches something called Vmax. It will never get over this Vmax. So Km is a point in this plot right here where the enzyme reaches half its maximum capacity. This is exactly what Km is, chemically speaking. But if you want to understand it in a better way, you can think of Km as the affinity of the enzyme to its substrate. It's like Kd that I explained like 10 minutes ago, Kd, which is the dissociation constant. So, as Km decreases, the enzyme is going to have increased affinity to substrate. And why is that? So, if you look right here, as Km decreases, you're gonna see that you also have decreased substrate. And when you have decreased substrate, this means the enzyme, all of them are gonna be empty. So when they're gonna be empty, they're gonna want to have their significant other, if you want to understand it like that. So their significant other is gonna be the substrate. So the lesser the Km, the greater the affinity is gonna be. Now, the greater the Km, if you surpass this, you're coming near the Vmax, the lesser the affinity, because the enzymes are already being occupied here. All of them are filled, okay? So they don't need more substrate, so they're gonna have decreased affinity. So that's exactly what Km is, okay? Now, since we derived the Michaelis-Menten equation, it's right here. V node is equal, V node means initial velocity. I don't know if I said that before. V node is equal to Vmax times substrate over Km plus substrate. So these are 3 points in the plot that I will explain right now. When S is equal to Km, which is right here, what is that? V node is gonna be equal to Vm over 2, which makes sense. At this point, it's Km, and Km is equal to what? Vmax over 2. And you can actually derive it from the equation, actually. S is equal to Km, you can do it mathematically. Now, when S is less than Km, so we're in this region, this is a linear line, and then it becomes a hyperbole. So in the linear line, S is less than Km, V node is gonna be equal to Vm times S over Km plus S, and S is negligible. Why? Because it's less than Km, so it's removed and it should look like this. It's a linear line. When S is greater than Km, which means that we're in this region, it means that we are reaching Vmax, where node is gonna be equal to Vmax. So how can you think of this mathematically? S is greater than Km, which means Km is negligible, which means these are mathematically they can be removed, and V node is going to be equal to Vm, and so on. Like this one can be done like this, and this one can be done mathematically. Most importantly, I really want you to understand these. Now, we're going to talk about Km now a bit. So when K2 is rate limiting. Now, what is K2? If you remember K2 from the equations, as we said before, E plus S, transition state, K2, E plus P, but this one's still early, so it doesn't have E plus P. So K2 is rate limiting, means that K2 is the slowest step in this whole reaction. It's the slowest step in this whole reaction, and the slowest step in the reaction actually determines the overall rate of the reaction. So what this means that if this one is slow, it means that ES is more likely to go back to E plus S, right? So when K2 is rate limiting, what happens is that ES is most probably gonna go back to its reactants, which is E plus S. Now, what does that have to do with Km? Since 5 minutes ago, we derived Km to be equal to K2 plus K minus 1 over K1. In this case, since K2 is rate limiting and it's very slow and it's negligible and it's still early, so it's not there, so we remove it. Km is going to be equal to K minus 1 over K1. But this is equal to Kd, which we explained in the beginning. Kd is the affinity of the enzyme to the substrate. Km is also the affinity of the enzyme to the substrate, but they're different regarding the presence of K2 or not. Now moving on to the Line-Weaver-Burk plot. So the difference between this plot and this plot is that this one is easier for the chemists. What they actually did, they took the Michaelis-Menten equation and they reciprocated it, flipped it, I mean. So V0 becomes 1 over V0, and these are flipped, the numerator and the denominator. And they made it a linear equation. The function, they made it linear, so y is equal to mx plus b. This is the slope, this is y, and this is the rest. And so why do they prefer this over this? Because in this plot, it's kind of hard to get an exact value of Vmax and Km. So what they did is that they made it linear, and the points of intersection to the y-axis and the x-axis are actually the exact reciprocals to Km and Vmax. Bi-substrate reactions. Bi is Greek for two, and substrate is the thing that's going to attach to the enzyme. So there are two types of bi-substrate reactions, type 1 and type 2. Type 1 is when the enzyme is bound to two substrates at the same time. So what happens is that E plus S1 in the transition state, another substrate comes, S2, and it binds to the enzyme and it forms something called a ternary complex. It's made up of three molecules, if you want to understand like that. And then E forms the two products at the same time. But the other type is when the enzyme works with one substrate, releases its product, and then binds to another substrate and releases its product. It does not form a ternary complex, no ternary complex. The enzyme works separately with each substrate. The last one is called a bi-bi reaction or a ping-pong reaction, because if you imagine a ping-pong table, it's like the balls coming forward and reversely, and it's exactly how this reaction is like. An example from your lecture is the transamination reaction by ALT enzyme. Transamination means that this enzyme, ALT transferase, is going to transfer it's just called ALT. ALT is going to transfer an amino group from, I think in this case, from alanine to alpha glutarate. Okay? So, CHO and CH2N2 are two coenzymes. And if you remember from the beginning, coenzymes are what? They are cofactors. In this case, they are organic cofactors that are derived from vitamins that help activate the enzyme in a couple of ways that I have aforementioned. CHO, I think, is pyridoxal phosphate, and CH2 and H2, I think it's pyridoxamine. Okay, so the enzyme starts with its coenzyme, and then the first reactant comes, which is alanine, or the first substrate. Alanine, the enzyme takes the amino group from alanine, and then it releases the product, right? E plus S gives us what? The product. So in this case, when it took the amino group from alanine, alanine becomes pyruvate. Pyruvate is released. And then the other coenzyme binds to it, and alpha-ketoglutarate binds to the enzyme, which is substrate number 2. This is the coenzyme, this is the substrate. So alpha-ketoglutarate is added to the coenzyme complex, and the amino group that's taken from alanine is added to alpha-ketoglutarate, and then the product is formed, or P2 is formed, which is glutamate in this case, and glutamate is released as the product, and enzyme is free again. Now, in your lecture, your professor mentioned rate limiting step of 2-step reactions and 3-step reactions. So a rate limiting step is the slowest step in the reaction. So the slowest step in this reaction is probably gonna be related to the enzyme forming the product, which is the case in both these reactions. So the rate limiting step in this reaction is this one, K2, which means that the ES is becoming E plus P, and in this one it's K3, which means that EP is becoming E plus P. And of course, if you want to get the Vmax, you're gonna have to have E total. E total. The total concentration of the enzyme is related to Vmax. You don't put ES. You put E total for Vmax. So moving on to factors affecting rates of enzymatic reactions. We have the concentration of H+. Now, what is the effect of H+? H+, the more H+ you have, the more acidic the pH is going to be. The less H+ you're going to have, the more alkaline the pH is going to be. So I don't know if you know this, but from 1 to 6 is acidic, 7 is neutral, 8 to... From 1 to 6 is acidic, 7 is neutral, 8 to 12 is basic. So the more H+, the lower the pH, the more acidic. The less the H+, the higher the pH, the more alkaline the pH. So H+ affects pH, and pH affects enzymatic reactions. So the optimal pH, or the best pH for enzymes to work, is between 5 and 9. And if the pH either decreases to 4 or increases to 10, this might lead to denaturation. What does denaturation mean? It means the enzyme that, for example, might look like this, it might become like this. And this is an inactive form of the enzyme called denaturation. So how does temperature affect rates of enzymatic reaction? The more you increase the temperature, the more you increase the rate. If you remember from the beginning, I told you to imagine the water. So the boiling water. So the boiling water, since you're increasing the temperature of the stove, you have the pot on, and the boiling water is right here, you can see the water moving. That's rate. So when you increase temperature, you increase rate. Now, if you increase the temperature way too much, this might also cause denaturation of the enzyme, which means deactivation. Now, moving on to something called enzyme catalysis. There are 3 types of enzyme catalysis. Number 1 is acid-base catalysis. Number 2 is covalent catalysis. And number 3 is metal ion catalysis. And I'm going to explain each one in just a second. So what is actually enzyme catalysis? Enzyme catalysis happens at the active site of the enzyme. At the active site, let's say this is the active site right here. And on the active site, there are certain amino acids that will bind to the enzyme transiently. When I say transiently, it means for a short time. And they have certain roles that I'm going to explain in a bit. They're divided to acid-base, as I said, covalent and metal ion catalysis. So in acid-base catalysis, what happens is that when the enzyme is reacting with a substrate, an intermediate can form. And this intermediate needs to be stabilized, because if they're not stabilized, this might ruin the whole reaction, okay? And I'll just explain it right here. So, as I said before, acid-base catalysis is related to accepting or donating a proton. And what is a proton? A proton is a hydrogen. So, a hydrogen is the stabilizer that's going to stabilize the intermediate that is formed, right? So, I'll reiterate. At the active site, okay, we have an interaction forming. An intermediate might form between the substrate and the enzyme. This intermediate is dangerous. It needs to be stabilized by something called a proton. If it's not stabilized, this might ruin the whole reaction and it might actually cause damage, right? So where does this hydrogen stabilizer come from? It might come from water, because water is H2O. So it might give us this or this. Depends on what we need. It might give us H3O plus if it's acting as an acid, or it might give us OH minus if it's acting as a base. If not, if water is not there, then amino acids in the active site, as I said, in the active sites, we have amino acids. They donate electrons or accept electrons. So it depends. Does this intermediate that I have lack electrons to be stabilized, or I need to pull electrons from this intermediate to stabilize this? It actually depends on the intermediate itself. So that's why it's called acid-base catalysis. So you can ask me, how can I differentiate proton donors from proton acceptors? Well, proton donors are those that haven't lost an electron. They are the ones that donate the electron. So it would make sense for us to see the electron in the, the molecule itself. So on the exam or whatever you see, if you see H in an acid, then most probably this acid is going to be a proton donor. Now, if you don't see an H, or you see minus, or you see these valence electrons, these electrons minus, then most probably this molecule has lost an electron, and is a proton acceptor. It accepts this H. So this can become, it was RCOO minus, right? But then this one donated a hydrogen, so it became RCOOH. It became stabilized. Okay? This is how you differentiate between them. It's probably very easy. And moving on,